Hello, everybody. Welcome to this talk about using C++ on ESP microchips. My name is Jakob Hasse. I'm from the Software Platforms department, and the last few years I focused on C++ usage inside ESP IDF, among other things. This talk will be structured into 4 parts. First, we will take a few benefits of using C++ over using C and see how users can use them, can benefit from them. We will also talk about the challenge when using C++. We will then take a quick view into the current state of C++ inside ESP IDF and seeing the repositories and examples involved. Finally, we will conclude with a roadmap, so what we plan to use, what we plan to implement in the near and midterm future. So in C++, you can use object invariants and the strong typing system to create something called strong value types. Strong value types should actually feel and be able to be usable like normal types, as for example, int. So you can copy them, move them around, but they have some advantages. One is they have only a private data member, and the constructor of that object can make sure that the private data member is always valid. So the value contained is always valid. Furthermore, you cannot convert them into another type. And that will get useful, as we will see in a minute. Let's first take a look at this class I2C master. It has a constructor, and the first 4 arguments have a strong value type. So if you want to use that constructor, you have to use it like this. You have to pass the actual type. You cannot, for example, pass an int 18, so just a raw int. You have to explicitly first create the type SCL-GPIO, and then you can use it. Otherwise, you'll get a compile error. But this usage is not the main advantage. It's much more useful if something like this happened. We accidentally swapped the STA-GPIO and SCL-GPIO. If we want to compile this, we will see a compiler error. It will say no matching function for call to what we are actually calling, and a note with a guess of the compiler what it thinks we want to call. And then it will directly tell us no known conversion for argument 2. We have some template instantiations here, but it basically tells us, hey, there's a SCL GPIO, and you're actually passing an SCA GPIO. Note that this is a compiler error, so you can correct that mistake immediately. If you would have used normal types as int or uint, for example, there would have been no error, so the compiler would have compiled fine. And you would have noticed that mistake only way later when you actually try to access the I2C bus. Another benefit of using C++ is automatic destruction and RAII. RAII stands for Resource Acquisition is Initialization. That means that each time you acquire a resource, you do that in a constructor. Each time you release a resource, you do that in the destructor of the corresponding object. We can see in this short appmain method how it's used. We have an I2C master object that we instantiate, so the constructor is called and resources are acquired. Then we write something to the I2C bus using syncWrite, master.syncWrite, and that's it. So before appmain returns now, it will automatically call the I2C master class's destructor, hence releasing its resources. So that means we cannot accidentally forget to release the resource, which is a big plus. Another advantage is that the same thing will happen if you return early because you notice an error condition. So you either return early using an error code, returning an error code, or you can throw an exception. In both cases, the I2C master object also goes out of scope, and the destructor will be called automatically. So again, you cannot accidentally forget to release resources or to incorrectly handle the error inside the function. So we basically have automatic resource management. Another advantage of C++ is that you can use C++ exceptions. It's a bit controversial, and we will see the different implications of C++ exceptions in a few minutes. But so first of all, let's look at the benefits. C++ exceptions cannot be ignored, so you cannot accidentally forget to check a return value of a function. If you ignore a C++ exception, it will automatically terminate the program. The same thing is true for automatic propagation. You do not need to do that yourself. It's done automatically. You do not need any boilerplate code to propagate error values. Neither can you forget to propagate error values. C++ exceptions are furthermore the only way to signal recoverable errors in constructors, because constructors do not return any values. And you also separate the error handling in the code from the actual code, from the normal logic, which means you have a cleaner and easier to read code. Finally, you can also use the C++ standard library. The C++ standard library is mostly operational in ESP IDF. Some features are missing due to missing underlying implementations, but the most common stuff is working. For example, you can use the containers library. You can also use threading and the synchronization primitives that we commonly use. Let's take a look at the challenge now. I will first briefly talk about the general code and memory size of C++. Then I will talk about C++ exceptions in particular. And finally, also mention some incompatibilities between C and C++. In general, C++ is built around a principle called the zero overhead or zero cost principle. That means two things. First, if you do not use a feature, then you will not pay for it in terms of code or memory size. If you do use a feature, however, it's implemented in the most efficient way already. So you should not be able to program a more efficient to program the same feature in a more efficient way using C or assembly, for example. C++ exceptions stand out a bit because, well, first of all, if you do not use them, you do not pay for them. But if you do use them, however, you have significant performance overhead in some situations. We will see the details later, but you can argue if it's the most efficient way to handle errors. So if we analyze the exception overhead, we can look at the runtime, we can look at the code size or the flash memory usage on ESP chips. We can also look at the stack usage and the heap usage. And that's what we are going to do now. To analyze the overhead, we use a little test program that does an element-wise division. So we have two arrays, and one is consisting of divisors and the other one of dividends. And it will element-wise do the division. And as soon as the divisor is 0, it will report an error. We have two versions of that program. One reports that error using exceptions. One reports that error using error codes. We run all these versions, each with and without provoking an error at runtime. All statistics are collected on an ESP32 chips, and we use all three commonly used optimization settings in ESP IDF. You can choose the debug setting, you can choose the optimize setting, and you can use the setting to optimize for size. Note, however, that this benchmark application is for demonstration purposes. In a real-world application, you will most likely not feel significant impact by both the positive and negative aspects of this of exception handling. If we look at the normal runtime, so if no error is reported, we can see that the version using exception is slightly faster than the version using error codes. And this is because no return values have to be checked. So checking the return values in the error code version takes time, additional time, and that's why it's slower. If we do throw an exception, or if we do need to report an error, however, the difference is significant. We see that throwing an exception takes more than 1 millisecond overhead. This overhead is dominated by throwing the exception, by the unwinding of the stack, by restoring the execution at the catch block. The error code example runtime is still dominated mostly by the calculation, because the returning of the return code of the error code is just a few instructions. If we look at the flash size, we see some increase. Part of that increase is because we need libgcc for unwinding the stack. So parts of libgcc or additional parts of libgcc will be used. And we also need handling information for each function that may encounter an exception. This information includes, for example, which destructors of local objects to call, as we've discussed before. If we look at the stack usage, if an error is reported, then we can see that that exception handling also uses a bit of stack. This is because throwing an exception means calling a few functions, for example, to a function to allocate the exception and a function to initiate the handling process, and that will call further functions, and all of them will also create some objects on the stack, and that's where this stack usage is coming from. If you do not throw any exceptions, then you will not have this overhead. We can also take a look at the heap overhead, and again we see that there's some additional usage if an exception is thrown. If no exception is thrown, then there won't be any overhead. The overhead is mostly due to the allocation of the exception object. Some of you may ask now, what happens if we throw an exception because we ran out of memory? In this case, the exception handling can use something called the emergency pool or emergency exception memory pool. You need to enable this in the menu config, but then you can use that, and that will allow to allocate an exception even if we ran out of memory. Another thing to notice here is that at this point, there are many kilobytes of heap allocated already. So the around 150 additional bytes are relatively small compared to the rest that is already allocated. So to conclude, if no exception is thrown, there should not be any runtime overhead. Use C++ exceptions only for recoverable error cases that are not in the main code path. In particular, you should not use exceptions to emulate control structures. Then you will have all the overhead because you're constantly throwing exceptions. There are numbers out there that suggest that exceptions should be used for events that occur at least or at most 1 every 100 times, or 1 every 1,000 times. Finally, exception handling does cost time, so do not use it inside interrupt service routines or for real-time critical code paths. Another challenge, which is minor but also plays a role, is that there are some incompatibilities between C and C++. If we have code that is called both from C and C++, we need to wrap the corresponding header files with extern C. Another problem is that in C and C++, the initialization of structures can be different. So if you take an example of IDF and try to compile it as C++, if it's not a C++ an actual C++ example, you will likely need to change the initialization of the structures there. Otherwise, you will get compile errors. Let's take a look at what we currently have when we want to use exceptions inside ESP IDF on ESP chips. In general, all the standard C++ features work. The standard is C++20. So everything that the compiler provides us should work. Also important is all IDF features. So all the components, everything you can call from the C code should also be callable from C++ code. If that's not the case, please let us know, because then we should probably fix this. We have two examples inside ESP IDF where the components are actually written in C++. These are NVS and the where leveling component. Inside ESP IDF, we do turn off C++ exceptions because we have a lot of users only using C. So they would not have a lot of benefit from using C++ exceptions, but they would bear all the cost. We also created a new repository called ESP IDF CXX, and this one should be easy to use and safe. So that were the main goals and main incentives. And in that repository, we do use exceptions because they have advantages. You can easily use constructors, and the code should be a bit more readable because you're separating the error handling. If we look at the ESP IDF CXX repository, we can see there are 5 examples, and they basically match the features we have in that repository so far. So the Blink example uses the GPIO classes. We also have C++ classes for ESP event, for ESP timer, for I2C, and SPI. Let's take a look at the GPIO example. I took the main function here. I removed all the comments, but you can find this very code directly in that repository. So it's not that long. So we first instantiate a GPIO output class. Interesting here is that you can see by the name that some of the configuration is inside the type already. So you cannot accidentally forget to set direction. And if you want to accidentally use the GPIO input class, you would also get compile errors because it has different functions than set high, set low. And as we discussed before, the constructor takes a strong value type GPIO num. The rest happens in the while loop. We just do set high, set low, followed by sleep for 1 second. And that's pretty much it. The rest is error handling. I hope this example gives you some insight of how few code is required to set something up with a new C++ repository and how easy it is to use, hopefully. And of course, if you have any contributions, let us know, and really feel free to check this repository out and give us feedback. We welcome all the feedback for that. Finally, the roadmap. We plan to publish this ESP IDF CXX repository as a component for the IDF component manager. We furthermore want to add more C++ classes until we have a minimal set of use cases that we cover. We plan to add some classes handling GPIO interrupts. We plan to add classes for ADC, PWM, Wi-Fi and networking, and possibly for general interrupt allocation. If we find that one important use case is missing, please let us know. We will consider it and maybe also add more C++ classes. But that's the current plan. So if you have any questions, please ask them now. We also have some references here for people who want to continue reading into some of the topics. Thanks for listening to this presentation.
Great. So now I'd like to invite Jakob to join us for the Q&A. Hello, Jakob. How are you?
Hello, Pedro. I'm good. Thanks.
So Okay, so I'd like to start by question. Why should I use C++ instead of C on my project?
Yeah, that's a pretty good question. So as the talk explained, there are certain advantages of C++. But what developers should definitely need to consider is that they need to be able to use them, right? So if you have someone who's written code in C for 20 years, they will not be suddenly able to write good C++ code. We've also seen the boundaries, right? We don't want to wait for an exception to be handled in while you're at the same time also serving a motor control, for example. But I think relatively simple projects can benefit a lot from C++, because C++ makes not only simple projects, but projects where maybe the real-time real-timeness is not overly important. Can benefit a lot from C++ if you have developers who are familiar with C++.
Okay, great. Do you have any kind of like recommendation, like if I have my project on C, like all my project it was written in C, and then I need to, or I want to move it to C++, how should I start doing that? Do you have any recommendation for that?
Yes, I would really recommend moving gradually. C++ is available in ESP IDF, but I would not recommend throwing over the entire project and then rewriting everything from scratch in C++. I would begin, well, certainly with the main component, write it in C, make sure that this works, and then you can gradually switch to C++.
Okay, great. So we have one from the community. Is there any benefit of using the STD sync thread mutex, etc., instead of FreeRTOS threads and mutex?
Well, you have the more abstract interface. You can, for example, run the same code on Linux or other machines that provide the libstd C++. That's the main advantage, I would say, and also that these the standard C++ library is based also around this RAII idiom that I talked before, which is good for automatically managing resources. So you can you have less chances of doing something wrong, basically during the resource lifetime.
Okay, I think we have time for one more question.
Mm-hmm.
How big is the overhead of using STD thread instead of FreeRTOS X task grade? Sorry.
Yeah, it's basically only the overhead of the libstd C++ and pthread, because our libstd C++ uses pthread, and pthread, or the pthread implementation of the threading library inside IDF uses the FreeRTOS tasks.
Okay. One more question. Memory allocations in C++ and can cause problems if engineers don't understand. Managing heap can be difficult on embedded systems with limited resources.
Yeah, well, first of all, it's a good question, because it's a common pitfall, memory allocations. First of all, it can also cause trouble in C if you don't understand how to use it. I would say in C++ it tends to be, if you're not doing the actual raw allocations yourself, but you tie the resources to classes as suggested in the talk, then I would say you tend to have a bit more safer code. Because you have automatic deallocations and all this maybe almost automatic resource management. Yeah, so there's some overheads in heap if you use the std C++, libstd C++. But that's something you need to find out in the application, how far you can go. But from a safety point, I don't see any additional issues in C++. Of course, you need to understand how the libraries work and how basic C++ works. Yes.
Okay, thank you for answering the questions. Thank you for the talk as well. And yeah, see you. Bye-bye.
Yep. Thank you as well. Bye.
Okay, so now the third block comes to the end, and we have a 10-minute break, and then we'll be back for the last block of the conference. Thank you.